Good morning everyone. So today we are going to discuss tutorial sheet 4, which is related to chapter 4, spanning trees. So the first question says that an edge E of a connected graph G is a cut edge if and only if it belongs to every spanning tree. So to prove it, first assume that E is a cut edge. Cut edge means that if we delete it, then the graph becomes disconnected. And we have to prove that it belongs to every spanning tree. We'll try to prove it by contradiction, which means that we assume that there is an edge E which does not belongs to a spanning tree T. Yes, now we have to reach to a contradiction, which means we have to show that E is not a cut edge if E does not belongs to an spanning tree T. It means that T plus E, because T is a spanning tree, if you add an edge to any tree, then it forms a cycle. So T plus E forms a cycle C. And clearly this edge E belongs to this cycle. And now if an edge belongs to a cycle, it means it is not a cut edge, which is a contradiction. Similarly, try to prove the other proof by contradiction, which says that you have to assume E belongs to every spanning tree. So E belongs to all spanning tree, and now it is required to prove E is a cut edge. Assume that E is not a cut edge. Now what does it mean if it is not a cut edge? It means that G minus E is connected. Now think how you will reach to the contradiction. G minus E is connected. So if a graph is connected, it means that it must have a spanning tree. So T is a spanning tree of G minus E. But G minus E has all the vertices which G has. And therefore T is a spanning tree of G also, containing so not containing E. T is a spanning tree of G not containing E, because T was initially the spanning tree of G minus E, so T cannot have E. It means we found a spanning tree which does not contain E, but it is assumed that E belongs to every spanning tree. So we start with a contradiction. E is not a cut edge, and we reach to a contradiction. So this is how the result is proved. The next question says that use Prim's algorithm to find a minimum spanning tree starting from vertex A. Prim's algorithm we have already discussed. So we keep looking for a minimum weight spanning tree, we keep building a minimum weight spanning, keep building a minimum weight tree until it results into a spanning tree. So starting from A, the minimum weight is 5. I reach to D. Now either I can go from A to B, or D to B, or D to E, or D to F. But the minimum is 6, so I prefer to go to D to F. Now next minimum is 7, so I go to A to B. Once I reach to A to B, again the next minimum is 7. I have to go such that it should not form a cycle. Now from there the next minimum is 5 among all possible, such that it is not forming a cycle. And next minimum is 9. You can say next minimum is 8 also, but if you add 8, this one or this one, it forms a cycle. So therefore you choose this one. And therefore this is how we get the minimum weight spanning tree. Total weight is 39. Prove that E is a loop. So recall that loop is an edge starting and ending at the same vertex if and only if E belongs to no spanning tree. So one side it's very easy. Please do try to solve it by yourself. So if E is a loop, it means that E is a cycle of length 1. And if it is a cycle of length 1, it means that it should not belong to a spanning tree by definition. A tree cannot have a cycle. So this side is very easy. Let's try the other side. Other side says that E does not belongs to any spanning tree, and we have to show that E is a loop. Again we'll try by contradiction. So let's say E is not a loop. Not a loop means it's an edge where starting and the ending vertex are different. In a loop they are same. So if it is not a loop, then T plus E would form a cycle C. Yes. Now in this cycle, if I consider T plus E means we add an edge E to the spanning tree T. Now T plus E minus F, which means you add an edge E to T and delete the edge F where F belongs to C. So T plus E minus F is a spanning tree because you add an edge which forms a cycle, and from that cycle you delete an edge, so again it becomes a spanning tree, something like this. Let's say there is a spanning tree, you add an edge here which is E and you delete this edge which is F, so it turns out to be again a spanning tree. So now T plus E minus F is a spanning tree containing E, but it has been assumed that E belongs to no spanning tree, which is a contradiction, and therefore E must be a loop. Prove or disprove: if T is a minimum weight spanning tree of a weighted graph G, then the UV path in T is a minimum weight UV path. So in graph G there are two vertices U and V. You found a minimum weight path between U and V, but at the same time if you find a minimum weight spanning tree and see a path between U and V, they must be same or must not be same. We have to prove or disprove. To prove, it need to be proved for all possible cases. To disprove, we need to come up with a counter example. So it's easy to generate a counter example. A, B, C, all edges have weight 1. Now consider, or instead of ABC, let's call it UV. Now minimum weight spanning tree is UWV, which means the weight is 2. But in the graph G, the length of the shortest path and its weight is 1. So therefore the above result is not true. Use matrix tree theorem to compute the number of the spanning trees. I am not doing it, but recall the matrix tree theorem. You need to find D minus A, where D is the diagonal matrix, where each diagonal entry represents the degree of each vertex. A is the adjacency matrix, so 0, 1 matrix in this case. You compute D minus A, then pick ith row and ith column, whichever you want, delete it, and for the remaining matrix compute its determinant. After computing it, please do verify the answer must be 392. Prove that Kn minus E, so Kn is the complete graph of order n. So if you delete an edge, any edge from Kn minus E, it must have n minus 2, n raised to the power n minus 3 spanning trees. Very interesting question. To prove this one, first recall the Cayley formula, which says that Kn has n raised to the power n minus 2 spanning trees. Yes. Now to compute the number of spanning trees in Kn minus E, what we can do, we can fix the edge E. We can find all spanning trees containing E and subtract it from the total number of the spanning trees. That gives us the number of the spanning trees in Kn minus E. So now each spanning tree, a spanning tree has n minus 1 edges. Yes, and total number of the spanning trees are n raised to the power n minus 2. It means number of edges in all spanning trees is n minus 1, n raised to the power n minus 2. But what we need is the number of the spanning trees containing the edge E. Now in case of complete graph, all edges have the same property, all have the same degree. Each one, so each edge is, you can say, the end points have the same degrees, and therefore to compute the spanning trees containing E, because of the uniformity, it should be n minus 1 n minus 2 divided by total number of edges, in Kn, which is n minus 2 by 2, and therefore 2 n minus 1 n raised to the power n minus 2 and n minus 1. This is very important step. Please think over it. And this is equal to 2n minus 3. And now we are done, because we know total number of the spanning trees and the number of the spanning trees containing E, and therefore Kn minus E has n raised to the power n minus 2 minus 2n raised to the power n minus 3 spanning trees. To verify it, simply try it. To better understand this, simply try it with K4. You can see that 16 spanning trees are there. Each one has 3 edges, so total 48 edges are involved. 48 divided by 6, because K4 has 6 edges, so 48 divided by 6 gives you 8, and then you need to subtract 8 from the total number of the spanning trees. So this is how you can verify this result. Next question says that for the graph below, assign these weights in two possible ways. First one, the minimum weight spanning tree must be unique, and the other one, the minimum weight spanning tree must not be unique. Easy exercise, but an interesting exercise. So here are the possibilities. In the first case, if you find the minimum weight spanning tree, then you go there 1 1 and you choose 2 2, because these are the minimum weight and it comes out to be unique. But in the second one, you can choose the weights 1 1, but now there are two choices for weight 2. If you choose any one of them, then again there are two choices for the next minimum weight 3 3. You cannot choose 2 2 because it forms a cycle, and it shows that there are at least 4 choices to have the minimum weight spanning tree. So it means in the other case it's not unique, but in the first case it's unique. The last question, and very interesting question, it says that A, B and adjacency matrix of a simple graph, and the sum of the diagonal entries of A cube is 24. Find the number of distinct cycles of length 3 in G. First, recall that what an entry, diagonal entry in A cube represents. So AII in A cube gives you closed walk of length 3 from VI to VI. So from, if you say 1 4 5, so from 1 AI, the number of the diagonal entries, represents the number of the closed walk of length 3 is starting from 1 and ending at 1. Now when it is of length 3, so only possibility is that it forms triangles or the cycle of length 3. You cannot repeat an edge because you need the walk of length 3 and it should be closed. So if you repeat an edge, it cannot be closed. It means that the total number of the closed walk of length 3 is 24. Out of these 24, we need to pick the distinct one. Now, if there is a walk like this closed walk can be present as 1451, but at the same time it can be present as 1541. Yes, both are closed walk, starting at 1, ending at 1. As a closed walk, they are different, but as a cycle, as a triangle, they both are representing the same triangle. Similarly, 4 5 1 4 or 4 1 5 4, 5 1 4 5 or 5 4 1 5, again they are representing, all these 6 represents the same triangle, but as a closed walk they all are different. So out of 24 there is a lot of repetition, or you can say that each closed walk or 6 closed walk are representing one non-isomorphic cycle of length 3. So in total 24 by 6, which is 4 cycles, 4 distinct or non-isomorphic cycles of length 3 are there in graph G. So that's all from tutorial sheet. We will discuss the next tutorial sheet, but before that we have to finish the chapter Eulerian graphs and Hamiltonian graphs. Thank you.